this episode, we shift from traditional compute instances to serverless and managed compute models, where you do not manage the underlying servers, but you are still fully responsible for how your code behaves. At first glance, serverless can feel safer because you are no longer patching operating systems or worrying about background services, but that impression can be misleading. The attack surface changes rather than disappearing, and the control points move from the operating system to permissions, triggers, and data inputs. Attackers target what they can influence, and in serverless systems that often means abusing event triggers, exploiting overly broad roles, or manipulating unvalidated input. Beginners sometimes assume that if the provider manages the infrastructure, security must be largely handled, but that is only partially true. By the end of this discussion, you should understand how permissions, triggers, and inputs define the real security boundaries in serverless and managed compute, and how controlling those boundaries reduces risk significantly. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Serverless compute refers to execution environments where you deploy code and the cloud provider handles scaling, provisioning, and underlying infrastructure management. Even though there are no visible servers to maintain, your code still runs somewhere, processes data, and interacts with other cloud services. That means your application logic, its assigned identity, and the events that invoke it are the primary security focus. Managed compute services follow a similar pattern, where infrastructure is abstracted but configuration and access remain your responsibility. The absence of direct server access does not eliminate the risk of compromise. It simply moves it into different layers. Attackers may not exploit a traditional system service, but they may exploit excessive permissions or poorly validated input. Understanding where responsibility shifts is crucial to securing these models effectively. Permissions are the first and most critical control in serverless environments because every function or managed workload operates under an identity. That identity is typically governed by Identity and Access Management, IAM, which determines what resources the workload can access. If a serverless function has broad permissions to read and modify multiple storage locations or manage infrastructure components, a compromise of that function can have wide impact. Beginners often grant generous permissions during development for convenience and forget to narrow them later. However, least privilege is even more important in serverless systems because functions can scale automatically and run frequently. A small vulnerability in code paired with excessive permissions can lead to large-scale damage quickly. Controlling permissions tightly limits blast radius and reduces the consequences of a code-level flaw. It is important to recognize that permissions in serverless systems often interact with many other services, such as storage, messaging, and databases. If a function only needs to read specific objects, it should not be allowed to write or delete them. If it only needs access to one storage bucket, it should not have access to all buckets in the account. Narrow scoping of permissions reduces the chance that an attacker can pivot from one resource to many others. This is especially relevant in cloud environments where APIs enable rapid configuration changes. When permissions are minimal and clearly aligned to function purpose, misuse becomes more obvious and more constrained. Tight permission design transforms a potential environment-wide breach into a more isolated incident. Triggers are the second major control point because they determine when and how serverless code executes. A trigger might be an HTTP request, a file upload event, a scheduled timer, or a message arriving in a queue. Each trigger type introduces different exposure and potential abuse paths. For example, a publicly accessible HTTP trigger exposes your function to the internet, which means input validation and rate control become critical. An internal event trigger may seem safer, but if upstream systems can be manipulated, they can indirectly cause your function to execute in unintended ways. Attackers may try to flood triggers, craft malicious event payloads, or exploit timing assumptions. Securing triggers, therefore, involves restricting who can invoke the function and under what conditions, ensuring that invocation paths are intentional and controlled. Controlling triggers also means understanding which systems are allowed to generate events and how trust flows between them. If a storage event can automatically invoke a function, you must consider who can upload objects to that storage location. If a messaging service triggers compute logic, you must consider who can publish messages to that queue. Beginners sometimes focus only on the function itself and ignore upstream systems, but triggers create implicit trust relationships. Securing serverless workloads requires examining the entire invocation chain. When trigger sources are tightly controlled and monitored, unexpected invocation attempts become easier to detect. Limiting invocation pathways reduces opportunities for attackers to activate code in harmful ways. Inputs represent the third major control area because serverless and managed compute frequently process external data. Whether that data comes from user requests, file uploads, or inter-service messages, it can contain malicious content. Poor input validation can allow attackers to inject commands, manipulate logic, or cause unintended behavior. In serverless models, this risk can scale quickly because functions may run concurrently across many instances. Beginners sometimes assume that using managed services reduces input risk, but vulnerabilities often reside in application logic rather than infrastructure. Strong validation, sanitization, and boundary checks are essential to prevent input from becoming an attack vector. Every input should be treated as potentially hostile until proven otherwise. Input control also relates to data size and format constraints. Attackers may attempt to overwhelm functions with unusually large payloads or malform data that consumes excessive resources. Properly configured limits on request size, message length, and processing time can mitigate these risks. Managed compute often allows you to define timeouts and resource caps, which serve as protective boundaries. These controls prevent a single malicious request from exhausting resources or causing cascading failures. When resource boundaries are well defined, denial of service attempts become less effective. Beginners should see these constraints not as inconveniences, but as guardrails that preserve availability and resilience. Logging and monitoring play a vital role in securing serverless and managed compute because traditional host-based visibility may be limited. Since you cannot log into an underlying server to inspect processes, you must rely on structured logs, invocation records, and permission audit trails. Monitoring should track invocation frequency, error rates, unusual trigger sources, and changes to permissions. Sudden spikes in function executions or repeated failed invocations may indicate abuse. Likewise, changes to the role assigned to a function can signal risk. Observability in serverless environments is about understanding behavior patterns rather than inspecting system internals. Effective logging provides the context needed to investigate anomalies quickly. Another important concept is minimizing environment variables and secrets exposure. Serverless functions often rely on configuration values and credentials to access other services. If these values are stored insecurely or exposed to unintended processes, attackers can harvest them. Managed secret storage services and secure injection methods reduce this risk. Limiting which functions can access specific secrets ensures that compromise of one function does not expose unrelated systems. Beginners sometimes overlook secrets management in serverless deployments because there is no visible server configuration file. However, secret handling remains a core security concern regardless of compute model. It is also important to address the misconception that serverless automatically isolates workloads perfectly. While provider-level isolation is strong, logical misconfigurations can still expose functions to unintended access. For example, overly permissive network settings or shared roles across multiple functions can create implicit trust between workloads. Proper segmentation and distinct identities help preserve separation. Designing functions to perform single, well-defined tasks also reduces risk by limiting their scope. When functions are small and purpose-built, permissions can be narrow and easier to audit. This modular approach enhances security as well as maintainability. Serverless security also benefits from the same baseline and validation principles discussed earlier for traditional compute. Even though you do not manage the operating system, you still define expected configuration states, such as which triggers are enabled and which roles are attached. Continuous posture checks can verify that functions remain aligned with approved settings. If a function suddenly gains broader permissions or a new public trigger, validation should catch that drift. Combining posture management with runtime monitoring creates layered defense. Predictable configuration reduces noise and makes unexpected changes more obvious. Ultimately, securing serverless and managed compute is about recognizing that abstraction shifts responsibility but does not eliminate it. Permissions define what compromised code can reach, triggers define how code can be activated, and inputs define what code must safely process. Controlling these three elements constrains attacker opportunity and limits blast radius. Monitoring and validation reinforce these controls by ensuring they remain effective over time. Beginners should internalize that security in serverless environments centers on identity and event flow rather than server configuration. When permissions are tight, triggers are intentional, and inputs are validated, serverless workloads become significantly harder to abuse. To conclude, serverless and managed compute models simplify infrastructure management but require disciplined control of permissions, triggers, and inputs to remain secure. Overly broad roles can transform minor vulnerabilities into major incidents, while uncontrolled triggers can expose functions to unintended activation. Unvalidated inputs can allow attackers to manipulate logic or exhaust resources at scale. By narrowing permissions, restricting invocation sources, validating data rigorously, and maintaining strong logging and posture checks, you create a serverless environment that is resilient rather than fragile. These principles mirror the broader themes of cloud security, where least privilege, predictable configuration, and continuous validation form the backbone of defense. When you apply those principles consistently to manage compute, you maintain control even as infrastructure complexity fades from view.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.